We will now have a presentation on Texiglass, and Luis Fernando is going to introduce himself. Good afternoon. Can you hear me? Wonderful. My name is Luis Fernando Tomás Barbie. I'm part of the commercial team of Texiglass and also work in development. And I'm here today to talk a little bit about our work with graphene and tell you what we see in the future and the advancements we have obtained with our project. This is just a brief summary to help us understand the topics we're going to address. So I'll explain what is Texiglass and who we are, our line of products and the industries in which we operate. And also I will tell you a little bit about graphene, the advantages and disadvantages of this compound, discuss the development of prefab uh, made from fiberglass with epoxy, resin, and graphene, and how this technology is helping us to improve the quality of our laminated products. Texiglass is a Brazilian company, and the head office in Zivinhedo in the state of São Paulo, founded in 1986. So, a new company, so to speak, in the area of reinforcement materials, with composites. We have the largest line of reinforcements and textiles in Latin America. We have more than 600 developments that we have completed to date since the beginning when we have implemented the ISO system in the beginning of the 2000s. And Texiglass is a partner of OMACO, Latin American Society of Composite Materials, SAMPI, the Society for Advancement of Materials and Processes in Engineering, and ABFIBRA, association concerned with the use of fibers in civil construction. As to our products, basically we manufacture textiles impregnated fiberglass, carbon fiber, and aramid, also known as Kevlar in the market, but we have other brands. We manufacture also fabrics, woven or unwoven, and multi-axle 0.90 or 0.45 without mat. We also distribute hoving filaments for pultrusion and other processes. We offer chopped filaments, impregnated filaments for the optical fiber industry. And also fabrics and our other products impregnated with resins, acrylic, phenolic, epoxies, etc. And these are some of the industries in which we operate. We are a very diverse company, so we operate in several different sectors and have a broad supply chain. We are in mobility, agribusiness. When we talk about mobility, we are talking about cars, trains, and airplanes, helicopters. In agribusiness, we go from machinery to technical products such as a pre-preg for a pulverizer. In civil construction, we supply chopped fibers, fiberglass mats, and also rebars made from fiberglass. In the energy industry, we operate in generation like the wind energy and also in transmission. In that area, several products made from composites are used due to thermal insulation. Oil and gas platforms have been manufactured from putrid materials, and this has been so for a long time. So fiberglass, epoxy resins, and others. We also operate in basic sanitation, or water treatment and sewage treatment, pipe manufacturing, and also in sports and industries in general. So, what is graphene? Many don't know what it is, and other people think it is something mysterious, and many of you already know what is graphene. So, I would like to talk a little bit about graphene from an industrial more than an academic standpoint. Graphene is a composite formed by hexagonal carbons. And we can see this in this figure. So it's a dust load that can be added to any type of material when the material is being manufactured. It's a very fine material, measured in a nanometric scale, 0.141 nanometers on average, and also measured by the number of layers. So we normally say that the less layers we have, the better the property the graphene can offer to your product. Graphene is also a very interesting compound since it's almost transparent. Of course, when we combine or when we mix the powder, it's black, as you see in this image. But later on, as you apply this material in an uniform manner, it's almost transparent. It's a very light and strong material with the largest young modulus ever discovered. So we are talking about 300 times stronger than steel. So we really can be used in different applications and can be very important for several markets. It's a very good product in terms of thermal and electrical conductivity. So it can be used in areas where we cannot have a lot of weight, and this opens a lot of possibilities of application in like the nautic industry where we need lightweight materials, and this is one of the major focus of our work, which is the manufacturing of conductive composites, material that's insulated but weak or has a good isolation properties but becomes conductive due to the inclusion of graphene. I believe you already know a lot about of the applications like paints and coatings. We see these paints that are very resistant, and this is because the porosity of the paint is decreased, and then it's easier to clean it out. Batteries. We have a new generation of batteries being produced in Europe and Asia, and these batteries have graphene in their formula, leading to a lighter product and also less need of room, like to be fitted in an electric car, which is a very hot topic at the moment. And lubricants. 4 years ago, I've been to Singapore and I visited a graphene manufacturer, and at that time, they already had a supply of 500 kilograms of graphene to a company manufacturing flexible mats and meshes. So graphene is already in our day-to-day life, and we don't know where it is, but it's already around us. And flexible is a reality. We are going to have these products so that we can benefit from this product. As any product, we also have disadvantages. I don't know if you have been informed about it. I just arrived, so I don't know what has been discussed by other speakers. but I would like to list some of the disadvantages that we observed during this 3-year development process, and we have 2 years more until we conclude it, to obtain high purity graphene with a low number of sheets. It's difficult to disperse. Identification of which solvent would be a better fit for graphene, or which would cause higher degradation, which would float up to the surface. We have performed several tests with different solvents until we could find the answer to these questions. The high cost of the material is also an important point, but we believe the cost will drop in time as production increases and more players will be interested in this product. Ease of handling, critical mass, technological maturity. We believe and we are sure that over time the cost will be less, and this will be a benefit for several applications. One of the major disadvantages is the high risk developments and low technological maturity. High risk is maybe the biggest challenge when working with graphene, because if it's high risk, we have several steps in development processes that we have to complete, and we have many obstacles to overcome. And if we don't have a good source of financing or a good partner who can help us as a company to support financially this type of development, many steps in this process can be just not completed or not even included in the plan. And when you skip one stage, it's difficult for you to go back and then redo all tests to achieve the same level of maturity. In particular, in the level of development that we require. So we are talking about a development that will take 5 years, from a morphological analysis of several types of graphene, how to disperse them in solvents, what is the speed that we should use in the ultrasound probe, the type of frequency. So all of these variables have been investigated, and we had to do that to reach to the outcome that I will present. As I showed you in the previous slide, less may be more. So the less, the more. In the case of graphene, and graphene, when used in large proportions, instead of increasing properties, it decreases properties. It's weird to say so, but I will show you what I mean. And the long development time is also a big challenge. How can I really fund all this development without being certain that this will, in the end, provide me with a product, or if the dimension I need will be achieved? And this is one of the biggest challenges that we have. Advantages, we've talked about the disadvantages. Let's say a few good words about this product, because it is a good product. Lightweight, weight reduction, and environmental impact. Improvement of mechanical and thermal properties. Flexibility and toughness. Lubrication and repellents, among others that are being developed. Just recently, we performed a very interesting work with impact resistance. A customer needed to increase the resistance to impact in his aircraft, and he couldn't increase the weight of the structure. So the epoxy resin with graphene, of course, in different proportions initially, made it possible to maintain the same structure for the aircraft to be able to land. If you're not familiar with this sort of aircraft, it's not tripulated, it doesn't land like a normal airplane. Normally it's a parachute that's open, And the purpose of this work was to increase the resistance to impact when the aircraft was landing. And we were very successful with this project, including all development stages. Texiglass is development. The work I will present now, and this is funded by FINEP, so Innovation Fund, National Innovation Fund for Research and Study. And 50% of the developments in this area is funded by this institution, including all these difficult stages, TRL1 to TRL6. So in maturity level scale 1 to 9, FINEP will support us between 1 and 6. This is a funding that we obtain through competition. When the topic of this study was one of the topics selected for development. The purpose, we as pre-pack manufacturers, fiberglass with epoxy resin, we had problems with the customer because that customer needed to insert several metallic inserts in the structure. Therefore, he had to increase the mechanical strength of the product without increasing the weight. In this case, the idea is to have a composite that is conductive. Instead of being an isolating composite, we need one that can conduct energy so that information can be exchanged. For example, from the beginning, the tip of an airplane wing to the other side. Normally we use cables for that, but the idea, of course, was to use graphene as a conductive mesh in this composite. And how did we do that? How are we moving forward this project? Using morphological analysis of graphene and dispersion, 7 different proportions and types of solvents, as I said, using thermal analysis, DMA, TMA, mechanical analysis, compression, strength, and shear strength. And right now, we are trying to find better methods for lamination. We could prove the improvements that we expected, and now we are coming to the lamination phase. Basically, this work included 2 methods to incorporate graphene into the matrix. The first is the incorporation of graphene using solvents. So we need a pre-dispersion with solvent, and then we mix with the resin, always using ultrasound probes and appropriate materials. And we can simulate this with different frequencies. And another method is by manufacturing graphene films using reduction in solvents, and then they are put under pressure, warm pressure. So this work is basically the lamination of a composite with enhanced properties. We've talked about the advantages, but what can we prove? This is an image that unfortunately is not very clear, but you're gonna have access to these slides and the FAPLA website. And here you can see electron microscopy test that allows us to see the dispersion of graphene using the method that we selected as the most important, with a future potential to be used in this application. So we were able to prove in several proportions of graphene or mixing rates. And what can we say? We have simulated some specimens, test specimens, and we have performed compression tests with pure laminate materials with no graphene, and then we simulated different mixing rates. So 0.01, 0.1, 0.5, and 1%.
The better resistant was the one with 0.01% of graphene in its formulation. There was 240 megapascals added. Actually, that moved from 240 to 262. So that's a 10% increase in resistance in a composite. In summary, the sample has the basic compression of 240, and by adding 0.01, we reach 262 megapascals. If we add 1% graphene, that drops, the resistance drops by 20%. Why? Well, because it becomes a strange medium in the lamination. When you have these parts and there are no carbon connections, the material will be divided instead of bonded. This is a material that can adhere to anything. Then there's this input about the different levels of graphene in the formulation and what it offers. So here, less is more. Shear strength. That's another Achilles heel. We know that shear is one of the villains in composites and lamination. So how can we increase resistance to shear? Graphene as well. So we had to work with very low proportions, because when we reached 0.5%, instead of increasing the property, it was actually decreasing the property. So we were decreasing lap shear strength. And when we talk about 0.01, 0.05, we add about 10 to 12%. And that has been lab tested. The whole proportion goes through an assay or a test to ensure that dispersion is uniform. Without uniform dispersion, it has been proven that the impact is opposite to the product characteristic. This is thermal resistance for epoxy resin. We did some TGA tests, DMA, TMA, and we saw some improvement in thermal properties. But this is still at its early stages when we think of mechanical properties for laminates. It is, of course, more interesting for lamination purposes. It's not that abrasive. In theory, there was not a lot of difference between the epoxy resin and then adding graphene. Finally, this is a reflection I wanted to bring you, which are the success points that we always take to developers, transformers. Texiglass produces raw materials for different industries. And we always want to share a message. And we want to have you think about this. So let me mention the successful points for composites. And this is connected to graphene. Well, having an appropriate development for the product, understanding demands, environments. It's important to understand all variables in the application so that you can design the appropriate development matrix. It's important to optimize processes and materials. When we propose adding a material to increase compression strength or lap shear strength, we're trying to optimize. We're trying to optimize the structure. Instead of a very huge mass of composite to support a specific load, just by using powder. And you might complain about this, but it is powder. It is very fine powder, albeit a noble powder. It ensures great properties, reducing weight, increasing properties, and finally, an appropriate production chain. There's no point doing all that if you don't adjust the production chain, the appropriate speed of production. So this is the triangle or the success tripod, we always say: productivity, cost, and performance. If these 3 points do not walk hand in hand, this cycle at some point will finish, either moving towards another composite or a competing product like a lighter alloy or steel. So that's my final message, and I would like to thank Vaplar for the invitation. I'm available. Our booth is D17 at Vaplar, and that's where you can see all our solutions. Thank you very much. Fernando, what is your perspective on graphene used for wind energy industry? Well, this material increases compression considerably. And since it increases the elasticity module, you probably are going to have rigidity. That allows you to decrease structures dramatically. Today in the wind energy market, they use carbon fiber spark-ups to support the mechanic load, external mechanic load. So it's compression, right? So this is an example of a possibility of improvement. Thank you. And regarding elasticity, what is the improvement that you noticed in terms of performance using graphene? Thank you for your question. About 10%. Studies are still at the early stages to understand the differences in materials and proportion, but there will come a point when we will focus on the module to understand how we can further improve performance. We have listed one single solvent for all properties for the time being, but maybe this solvent might decrease the module and dispersion. So there might be a more appropriate solvent for this property. That's why it takes time to further develop. Do you have any specific development for the elasticity module to apply to rebars? No, we don't. The assays or the tests we've conducted, these are lab tests to prove some improvements, but we haven't reached the product level yet. This is still the transformation stage. We've moved already from the dispersion stage. We are in the lamination phase, and we have proved some things for lamination. But now we want to replicate that in the product. We are looking at infusion, layup, compression, because we want to understand the different properties. So we're going to simulate the processes.